Students, so today we are going to discuss electromagnetic theory of radiations. Now, first of all, what do we know by dual nature of electromagnetic radiations? Dual means double. Dual nature means double character of electromagnetic radiations. Now, which way it is double character? That these rays possess wave nature as well as particle nature. So if a particular radiation possesses wave nature as well as particle nature, then we will say that this wave or this radiation shows dual character or dual nature. Now as far as electromagnetic radiations are concerned, they show dual nature. Now in today's session we are going to discuss about first thing, that is wave nature. How can we say that electromagnetic radiations possess wave nature? Okay, so James Maxwell was the scientist who suggested that when electrically charged particles they move under acceleration, okay, then alternating electric and magnetic fields are produced and transmitted. These fields are transmitted in the form of waves, okay, and those waves are termed as EM waves. We can simply write EM waves or electromagnetic waves, okay. Now, so what was told in this paragraph, that James Maxwell said that whenever a charged particle moves under acceleration, then it produces electric and magnetic fields and transmits them, okay. Now the transmission is in the form of waves, okay. Those waves are called electromagnetic waves. He was the first to reveal that light waves are associated with oscillating electric and magnetic character, okay. So he was the first who said this. Now, what are the different postulates of electromagnetic theory of radiations? So very first postulate is that electric and magnetic fields produced by oscillating charged particles, they are perpendicular to each other, okay. This is just like x and y axis. You can see in the paragraph that if this is your x axis and this is your y axis, then if we consider the magnetic field component towards x axis, then y axis will represent the electric field component, okay. Both will be in this way perpendicular to each other, okay. Now, so what we can say? We can say that very first postulate is that these waves consists of electric and magnetic fields which are perpendicular to each other, okay. This way we can say this first point. Now one more thing is that whatever is the direction of propagation of the wave, now see, this is the source from where the waves are originating. Now this is the direction of its propagation. This is the direction of propagation. If we see this magnetic field, that is also perpendicular to this. If we see electric field, this is also perpendicular to this. So the point is that to the direction of propagation of wave, electric and magnetic fields both are perpendicular, okay. Now second thing, we know that sound waves require medium to travel. If there is no medium, then there will be no sound will be heard, okay. But in this case, if we are dealing with electromagnetic waves, then there is no need of medium and they can easily move in vacuum, okay. So here you have to learn these two properties. There are few more properties, two more are there, but one by one we are going to do it. So these two properties are there. With these two properties you have to draw this diagram also, and these two properties you have to remember. Now the third property, it covers a lot. Now it is now well established that there are many types of electromagnetic radiations which differ from one another in wavelength or frequency. These constitute what is called electromagnetic spectrum. Different regions of the spectrum are identified by different names. Okay, now see, this thing is electromagnetic spectrum. This is visible spectrum and this is the whole electromagnetic spectrum. Now see, in electromagnetic spectrum what we have done. There are two properties which will come in the fourth postulate: frequency and wavelength. Okay, now see, if you see wavelength, this is wavelength. If you see, when we are moving from this end to this end, there is increase in wavelength. Wavelength is increasing. But if we see frequency, it is decreasing from this direction to this direction. So it means that frequency and wavelength, they are reciprocal to each other. Okay, if one increases, that means the other decreases. Okay, now what is electromagnetic spectrum? Here one thing came, electromagnetic spectrum. As I said, this is the electromagnetic spectrum. So what is this? This is the arrangement of different rays in the increasing order of their wavelength or decreasing order of their frequency. Okay, that particular formation is called electromagnetic spectrum. So how we can define electromagnetic spectrum? We will say the arrangement of all the electromagnetic waves in the increasing order of wavelength or in the decreasing order of frequency is termed as electromagnetic spectrum. Now see, few examples are given. Radio frequency region is around 106 hertz. Hertz is the unit of frequency, meter is the unit of wavelength. Okay, now this frequency, this is called radio frequency. Why? This is used for broadcasting purposes. Okay, microwave region 1010 hertz, used for a radar. Infrared region used for heating. Ultraviolet region component of sun's radiation. Okay, so this way there are so many examples. Now this part of this spectrum, we have elaborated it, we have taken it out this way. So it ranges from 400 nanometers to 750 nanometers. Okay, this nanometer you have done earlier. Nano stands for 10 raised to power minus 9. Okay, so wavelength varies from 400 to 750 nanometers in case of visible region. Visible region means which we can identify with our eyes, which we can see, which those frequencies or wavelengths which we can identify, which we can detect with our eyes, that is called visible region. Okay, now this was a third postulate, where what we will be saying that there are so many electromagnetic radiations which differ from one another on the basis of wavelength or frequency, and collectively they are known as electromagnetic spectrum. Okay, this is our third postulate, and this way we have to make our electromagnetic spectrum also. Now fourth point is different kinds of units are used to represent electromagnetic radiations. Okay, now see, there are four properties mainly. Here in this slide we are going to discuss three properties. First is frequency of electromagnetic radiation. Second is wavelength of electromagnetic radiation. Third is speed of light. Okay, now these three are interrelated with each other. So what we can say in this point, we can say that any electromagnetic radiation has some definite values of C, nu, this is called nu, frequency symbol is nu, C, nu and lambda, this is called lambda. Lambda is wavelength, c is speed of light. Okay, now what is frequency? Frequency is defined as the number of waves that pass through a given point in 1 second. Now see, suppose this is the source, and from here waves are going. See, this is the source, and from here this way our waves are going. Then suppose this is the point where we are seeing, where we are observing. Suppose 10 waves pass in 1 second from this point, then we will say the frequency is 10 per second, or we will say 10 hertz. Okay, so this way we have to do it. So frequency is number of waves passing through a point in 1 second. It's denoted by nu, and its units are either hertz or second inverse. Similarly, wavelength. Wavelength is denoted by lambda. And what is wavelength? It is the distance of two nearest neighboring crests or two nearest neighboring troughs. Now see, when we talk about a wave, motion of a wave, then see, this is called crest, this is called crest, this is called trough, this is called trough. Now whatever is the distance between the two nearest neighboring crests or between two nearest neighboring troughs, that will be same always. That is denoted by lambda and is called wavelength. So since it is a length, so its units will be the units of length. So its units in SI units are meter. Okay, now third thing, speed of light. Now as we discussed earlier, that these waves do not require any medium. So in vacuum, let it be any radiation, whatever is its wavelength, it will travel with the same speed, and that speed is speed of light, which is taken as 3 into 10 raised to power 8. This is 10 raised to power 8, this is 10 raised to power 8. Okay, so speed of light is denoted by c, and it is 3 into 10 raised to power 8 meter per second. Okay, and it is the speed which will be possessed by all electromagnetic radiations, whatever is their frequency, whatever is their wavelength. Now these three things are related with each other by the relation c is equal to nu lambda, and this is applicable for numericals also, and you will be asked numericals on the basis of this. Now one more property, wave number. Now here, what is the symbol? We write nu first, and then we have to put a bar, and what we will say, nu bar. Nu bar is the symbol of wave number, and it is equal to, nu bar is equal to 1 by lambda. It is the reciprocal of wave length, and it is called wave number. Okay, so now what should be the units of wave number? Since it is length inverse, so its units will be meter inverse. But since wavelength is not very is not having large value, so because of smaller value we use this centimeter inverse, and when we are using centimeter inverse, then it is not SI unit. This you have to remember. Now let us discuss one problem. The question is, the wavelength range of the visible spectrum extends from violet 400 nanometer to red 750 nanometer. Express these wavelengths in frequencies. Okay, now see, in this question we are given with wavelengths, okay, of the visible region. Visible region wavelength is given. Now we have to convert it into frequency. Now we will be using the term c is equal to nu lambda. C is equal to nu lambda. Now since c is fixed, having fixed value, and we are given lambda also, so we have to calculate nu. So nu will be equal to c by lambda. Now here we are using this relation. C value is this. For first 400 nanometer, it is 1 nanometer is 10 raised to power minus 9. So units up are meter per second and down they are meter. So meter will cancel, we will get second inverse or hertz. So we will be getting the value 7.5 into 10 raised to the power 14 hertz. Similarly, for 750 nanometer, we will be getting value 4 into 10 raised to the power 14 hertz. So what is the range obtained? It is 4 into 10 raised to the power 14 hertz to 7.5 into 10 raised to the power minus 14 hertz. Okay. Now whatever we have discussed only one nature. Our topic was dual nature, and we discussed wave nature, and related to wave nature whatever components were there, those were discussed. Now on the basis of this, you have to solve these home assignments. Okay, thank you.